Hello and Assalamu alaikum everyone. I'm Assam Aslam. So today I will tell you how we can master OpenSees. OpenSees is actually basically a software uh, developed by UC Berkeley. So it is mostly used for civil engineering and structural engineering. So OpenSees actually when they developed it, it was initially they used TCL, Tcl. It is called Tcl. And then they, because it is a very complex language, it needs much more variables. So then they also converted to Python. So I will give you a little bit introduction. This was a course offered by Shinhua University in China by some professor, Italian and other professors. So all credits to them. But I will explain you briefly one detailed example, and then I will show you multiple things like trusses, beams, trusses and columns. There are some also related to geotechnical engineering problems, and also some pushover curves, model analysis, damping ratios, how to calculate. So this course contains all of this information. So if you practice any of the example, and also there are some exercises in it. So let me just give you a small and brief introduction. So Tickle was developed by Dr. John Ost- Osterhout while he was like a university at Berkeley University. So it is pronounced as Tickle, tool command language. So basically, it was developed to create a language that can be embedded into other program easily and then extend its new functionality. So it's a position-based language, not a keyword-based language. Then Python, obviously, you know all of it. It's a basic of all programming. Like MATLAB is a different thing, and Python is a you have to let's say you don't need to. This is an open source MATLAB. You have to buy MATLAB first, provided by universities or whatever. But Python is open source. You just install Python. So Python has an edge in this. Um, you can say in this field. Then OpenSeas was this was one of the PhD student at UC Berkeley. So it was during his PhD he developed OpenSeas, and then OpenSees Pi, one of his student uh, developed this. So you can see this is a Tcl language and this is OpenSeas. So usually if you see very quickly, it looks similar. But if you see here, if you want to compute an area, it is Python is much more simpler. But here you have to first use more complex languages. Tcl. So then these are special characters. I will this PPT can be shared with you, so you can read it by yourself. I will just briefly go. So recorder is um you can say where we can analyze the results for OpenSeas, whatever like displacement, forces or whatever. So that is that thing. So if you didn't install OpenSeas, I have also another video on my channel. You can just follow that. It needs Python 3.8 or and these are like also that they if you just want to use spider, that is an easy way. You just install anaconda prompt, and you just install by through it. But this is another way you can also follow this. See, make this is this optional Visual Studio. It is also free software. You can just install an API. This is also free. So let's go towards an you can see this is a complete course, 4 day 2 day course, 4 sessions, complete videos, and there are some also. I will just simply go through one detailed example, and then because the if I go through one mm, detailed example, all other examples of the pattern is same, but they are just different, like um what to say, beam trusses or whatever. So let's see frame. I will just explain this one. let's say frame elastic. If I open this one, I open spider. Okay, open this one. I think it couldn't load it. Okay, okay, this is now here. So in Python, if you want to make this as a current directory, so you what you do, you just like copy this address and cd directory space address and run it. Then see this is your current directory. So let's run it. Actually, first of all, let me explain what each code will be like, what will be the structure of each code. First of all, it is a simply 2D elastic frame with two beams and a like two base fixed bases and a rigid beam across the top. So if I just run it, you can see that the simple 2D beam. So these are the shear forces and these are bending moments and deformed shape, and this is it's showing horizontal load being applied on it, and these are nodes. So see, uh, I will just let you know how it can be written. First of all, uh, first thing is that you have to do imports and setup every like every code. You have to import OpenSees and OpenSees matplotlib if for plotting. So you have to import. Actually, this is a solver. Then OPSVIS is the plotting for like matplotlib, and then output is created for and this output is created for the results recorder folder. Like this should be for the recorder folder. So first of all, you create record output folder and then also import the libraries. The second thing is that here he is defining the geometries and properties. So you see here L1, L2, the like lengths, column height, and then bay width, and then cross section height and width. Then elastic modulus, area. He's calculating area, and he's applying 10 for 10. So one more thing, like abacus, it is also a unitless. Like it doesn't have any units. Whatever you put, it will follow that unit. Then the third thing is modal definition. In modal definition, actually, a number of degrees, and a number of degrees and nodes, and then he's defining elements and sports like fixed sport and bound. See, he's fixing the boundary condition and node and elements. Then he's applying loads. For the load, he's applying linear and linear uh, in a plane load at the node 3. Where is the node 3? Here. He's applying here. And then what he's doing, I told you, the recorder. Recorder, what actually do it, if you want, whatever you results you want to see, displacement, reaction force and bending moment, whatever. And then after that, what kind of analysis you want? Like constraint plane, good for mostly static models. Then number, here number. This is simple degree of freedom numbering. Then system, here if you see system, then it is symmetric positive defined and like linear elastic, whatever. And algorithm is linear, and then integrator, that is apply full load in, actually if you want to apply full load in one step, then it will be integrator. So then it just quick checks if print if all the model is well, then it will just have a quick checks, and then it check the compatibility with OpenSees and shims. So actually it check if there are any errors, then it checks if there are any nodes to be fixed or number of degrees of freedom or whatever. So this is the overall structure of the code. And then the plots, like whatever, which plots do you want, shear force, bending moment, axial force, and whatever. So this is the general structure of the code. Every code will follow this one. So you can see here, this is a 2D elastic frame, and then this will follow the same code. in every model. Or I will go through other models also quickly, but that I will not go because the detail will be same. Okay, let's say now we go with the truss. So that is an identical language. Okay, so this will be the truss. Like I will. This is so you can see it's a simple truss fixed as one and roller support another, and the stiffness is calculating stiffness. So let's see. We like open this one. So you see here the like structure is also same. First of all, he is importing the packages, then he is creating output and inputs, defining inputs, model, then like boundary conditions, and this is a simple trust actually. Then loads, recorder, analysis. So every code uh, the structure of the code will be same. So this is then if you run this, so you can see here. So this is a simple trust actually, and you can see here deformed shape. This is a like he's telling okay what is this code like what kind of structure it is, and then this is a triangular truss actually, and it is giving us a deform deformed shape and then axial forces. So then if we open other this one, let's say elastic, let's say what is okay, this is a simple like a simple one 2D the 2D truss also. This is a simple 2D truss, and yeah. So this is also giving us a axial forces like whatever. So 2D truss bar actually. So a fixed port at the end and subjected to horizontal load. See horizontal load. So then we open. It's actually this is like looks like a cantilever beam. So you can go through with these example. Then let's say open the beam. I will just show you further. You can go through all if you want to like practice this as completely this code. You can have the access of this uh, course. There are also some exercise courses. Okay, let's see what is this beam. Oh yeah, so this is a simple 2D cantilever beam clamped at one end, and this is a bending moment. This is shear force, axial force, deform. So see, actually, fixed at the base end and the nodes to the actually rectangular section, they are applying the tip load on the second end. All right. So see, this is a beam, and let's say I think we already checked this one. Same elastic, same. Okay, let's see. Now we see the beam and truss, a combination of both beam and truss. So let's see how like this looks like. It will be, I think, truss both. Yes, this is a simple rectangular truss. Okay, it will be like look like this. Okay, let's see. It should be. If we run this, see. Uh, so here this is actually axial force is the same thing but a different structure. So yeah, so this is actually a combination hybrid model for the trusses beam, two trusses beam and column. So you can go through the structure is same for all the codes. If you want to practice it's a very good like for you. Okay, so then it's same as saying we see this is 3D beam. I think there is some type of something. wrong with it, it needs to be fixed. Okay, so then, so this is uh, okay. Also, these are for your exercises. If you want to master this course, let's say, so these are hand calculations. But if you want to do it through OpenSees, let's open this one. Okay, so you can see it. Let's verify one thing like with 3 5 here. Yeah, it's matching with the hand calculation. So you can see that if you want to exercise, if you want, you can also do some exercise with it. The solutions are provided here. So the second thing, okay, let's go the second session here. Professor Fabio from Polytechnico, Vertical Python. You saw that. So this is their official website. You can follow. So you see the code structure, materials, cross sections, then elements, then loads and masses, then recorder, and then plots. This is a simple column. Okay, this is for the pushover curve. Okay, let's see if that code runs or it has any problem. I think it should be okay. If code has any problem, just you can take help with the chat GPT also. It can fix the code for you. Okay, okay, let's open now non-linear. Okay, so you see here, this is a 2D frame. It is giving us all the displacements and bending moments. Two-story frame. Here is now two-story. This is pushover curve for this one, and this is deformed shape. All right. So you can see these are two different kind of frames. This is a steel mesh, I guess. Yeah. So you can just go through in detail when you have the access of this. So let's say open this one exercise code. Exercise one. Oh, I think this is only taken. We need to open. If you have tickle, you can also let's say okay push over curve. Okay, this is in push over curve. Yeah. Okay. Yeah. So this is so you see here it is giving a push over curve. Simple structure. So what is this? Yeah, you can see different exercises and have practice more practice. Okay. So see, so this is uh, yeah. So this was all discussed in this one in this slides. The same thing for the theory concept. Hmm. Okay. Then if we go to morning second day, so this is I guess yeah. So this is a different professor, no, the same one. Model analysis. Okay, model analysis and damping issue. Okay, okay. So this is how to calculate through eigenvalues, damping, mode one, mode two, and then this is a damping. So yeah. Okay, we can also see this if this code works. We have some issues. Okay, let's see. Okay, this is model analysis. It should give us some values like mass participation or something like that. Okay, so here it is giving them first period eigenvalues, mass participation ratios. Okay, and let's see what is this. Okay, damping analysis. So if we run the damping analysis, it should give us Okay, so by eigenvalues means zeta and t minimum. Okay, it is giving, and also the plot. Hmm. And the time history it should create, I guess, the time history series of load. Yeah, so different. These are the different examples. So it created the different time series load for you. So then you can implement this eh, in your code. Time series, same thing. So this is Tcl, not the Python one. And then if you go the last version 23, they're also recording detailed recording for this one if you want to have the access. Afternoon. So this is I think it's not okay. That is the same time series. It will be same. It will generate time series. This is a share wall. This is not, but in Python. So yeah, so these are the related to I think geotechnical engineering. If your background is from geotechnical engineering, in this one course is soil foundation structure interaction system. So code is mentioned in this one. You can just follow this. Okay, fluid solid coupling. All right. It's the same thing. Yeah. So these are all the these are all the if you just understand this one core structure and then apply it to different things like different trusses elements or whatever according to your code. So it's available in both Tcl language and also in OpenSees Py. So it's very useful course if you want to have practice OpenSees. If you practice all of this, you can do any problem. So please ask me if you have any question. Thank you.